So welcome back. We have just seen how the random walk was handled by the platform. Now let's see what's coming next. So before moving to the other aspects related to control, in particular to tuning at best the gain in our controller, there was some intermediate experiment that was made in Tübingen. You may remember that the whole purpose of this is also one of the purposes from a perceptual point of view, from a biomechanical study perspective, is to see how, if and how the user changes his way of locomotion when moving on one of these platforms. And so far, only linear motion has been tested. So the 2D platform was intended to see what happens in the two-dimensional omnidirectional case. Another attempt was made in order to design and, let's say, see a concept of pure angular motion, so a 1D circular treadmill. This was not further developed, but it's nice to see what happens in these cases when we have such a behavior. And here you will see Professor Bulthoff, who was the head of the Max Planck Institute for Biological Cybernetics in Tübingen, walking on this platform. So you see that this is rotating and he's walking, so in fact he's rotating, he's walking in place. If he makes a bit longer steps, he will advance. This supporting table was meant to give stability. Of course, this is just a test, let's say an open loop test. There's no controller here. The platform goes at a certain speed and the user accommodates, while in fact it should be exactly the opposite. So you walk at some speed and the platform accommodates so that you stay in place, or you move forward or backward so that you experience some angular motion. And this was the whole idea. We have seen that the linear platform, no matter if one-dimensional or two-dimensional, do not produce a rotation of the orientation of the walker, while this circular treadmill will do the job. Of course, this was kind of a nice situation. Okay, so how do we proceed from here on? Now it's important because already with the one-dimensional platform, we started making some integration tests. So integrating the fact that the platform is moving, the user is moving. Why? Because it's exploring a virtual world. So let's spend a few moments on talking about this component of the project, which is also interested for the immersion VR. One partner of the project, as I said, was the ETH Zurich, the group from Luc van Gool, and they, a group of researchers developed a method for creating architectural images of cities. And in fact, they just not put together some CAD models, but created a procedural language which uses architectural rules which characterize the style of construction. It could be ancient Rome, it could be Greece, it could be New York, it could be a traditional city in South Germany, and so on. And from a set of rules, in a quite fast way, you could reproduce using some map, let's say a 2D map of the place, adding the rule and generating in a relatively short time a full 3D representation. This 3D representation can be then saved and stored in some high-powered computer and then being explored either through a joystick or, in our case, through your intentional locomotion on the platform. You see that you can render different level of accuracy of details in your homing. And here you see 3 examples exactly from houses which were built according to the traditional Roman architecture of the 79 after Christ. Ancient Pompeii was reconstructed for CyberWalk, but other attempts were done, and there's a famous way of saying that Rome was not built in a day, but in fact it was rebuilt in one day using this CityEngine. And I have here a nice video. CityEngine, after the end of the project, became a spin-off company from ETH Zurich, so sold this product. And here you will see some performance of CityEngine. There are two views of a city, and here it's a modern, let's say, Manhattan-style profile. Each building has been set up with rules. There are some similarity, there are some changes, dimension of windows, styles, and so on. And in fact, what they did is they took the plan of Zurich, which is on a lake, and constructed Manhattan on the map of Zurich. And also, they reconstructed the ancient Pompeii. This is a typical impluvium, so it's an open area at the center of the Roman house, typically with a small pool collecting rain and with a cloister inside. And here you can see the view of Pompeii from above. Of course, if you walk, you will be in one of the streets, and you can enter the building, walk along, go to the right, to the left, go return back, and so on and so on. Of course, this requires quite computational complexity in terms of evaluation of millions of vectors in this rendering of images. This is why you can have, for far distance buildings, less resolution and higher resolution as soon as you get closer to one of these buildings, you enter a door, and so on. Okay, so what is needed for doing this? Indeed, the Vicon. The Vicon localize the helmet, your head. You see here this 7-ball support that you can move around. Here you see one of the students that were doing some tests. The Vicon system itself is quite expensive. These are old data, but has a possibility of updating position and orientation at the frequency which is above 120 Hertz. The accuracy can get closer to 1 millimeter of position and to 0.1 degree in orientation. Of course, you can use roll pitch angles or Euler type angles for the orientation in this sense. So when you put everything together, as I said, you should you are certainly interested in having a nice rendering as if you were not walking, just sitting in front of your image, your computer, or wearing a helmet, sitting somewhere, moving the joystick or moving your head around. And this is already a traditional way of doing VR immersion and visualization. The additional step here was the fact that the user was walking. And in fact, you should map this motion into the virtual world, together with the different view that you can assume, both standing still or walking and looking around in a very natural and unconstrained way. So here you see an overall view of the system. It's a flow chart in a sense. You can recognize on the top left part the Vicon tracker. So you detect the marker. The marker are these balls mounted on the head of the target user. So you reconstruct, you generate the trajectory from there. You have a CityEngine which generates the model with geometrical parts, texture, details, architectural, and you have another part which, using OpenGL, does the rendering and then displays this either on a beamer, so on a screen, or on the head-mounted display. And on the top right part, you have now the CyberWalk application, which, as I said, takes uses the high-level tracker for localizing the user, and then the platform control will move the platform accordingly, so that the rendering application should know the position of the user and the speed of the user as resulting from the platform control, so that it can subtract this information, and what remains is purely intentional motion, and this part should be used in order to let him navigate in virtual reality, modifying the level of detail. So there's a condition from the CityEngine high-resolution environment, there's a multi-resolution conditioning, so closer objects are described with more detail than farther objects, farther with respect to the point of view of the user, of course. The head orientation is being tracked, so the head tracker is the same that is being used for localizing the user and doing platform control, and everything boils down into the proper image being updated in the head-mounted display. You can see that all this, let's say, synchronization is quite critical, otherwise the feeling would be completely lost because of walking. So we made the first integration test using the one-dimensional treadmill. So before the completion of the construction of the full 2D platform. And here are the first results. It's May 2007, so many years ago right now, but it was less than 1 year to the end of the project at that time. The contributors are coming from different partners in the project, and here you will see a first view of what's going on. You can hear also some sound. So this is Ilya is walking on the platform. You see the platform is the same as before. You can hear the sound of the motor and of the platform itself. Now you see that the reconstruction is not yet complete. He's stopping, he's looking around. The update is, you can tell the number on the left, about 10 to 20 frames per second of update. You see a huge number of vertices being transformed at every instant of time. So he's stopping and looking around. While he walks around, the view changes. You can see some entrances. Of course, this is just a preliminary street of the ancient Pompeii. There's nothing beyond. There's not even the volcano, the Vesuvio. So just at that time, this was just a preliminary check that everything was working. So treadmill control and visualization at the same time. Now, let's turn back to the control. Let's see what happens when we are trying to tune the platform. Now, these steps that I will go through rather quickly, I hope, are intended for any system where you have a model, you design a control law based on the model, then you check it with respect to the real system, and then you go back and you update and you do fine-tuning and so on. So the same thing was done for our kinematic control of the platform. So the first step is you design the controller in the ideal case. You assume that since you're commanding velocities, for instance, or acceleration, your commanded velocity are exactly the actual one. So there's no dynamics of the target system which shift the actual realized motion with respect to the commanded motion. And you don't have saturation, neither in acceleration or in jerk nor in nothing. So this is the first step, the one that you can do on paper, and then you can do some simulation. Now, in this, of course, you have two parameters to choose in your control law. In our case, a number of gains, K1, K2, K3, KW, and kx, kb and kx, and then also a gain related to the mobility of the x reference position for the controller. So you do some trials with gain, you may have some rules, some pole placement techniques to choose them, but once you're satisfied, you do some experimental tests. And the nice idea here, the nice idea here is that you can do experimental tests already with a control loop closed on your real system. You know that identification of the actual dynamics of the system can be done open loop, so you generate commands and you collect data and you try in a parametric model to fit in the best parametric value that reproduces the data that you have collected in your testing experiment or identification experiment. Here you do exactly the same, but you apply already your target controller with some nominal, the best parameters that you have. This is good and bad. It's bad because you're not exciting the full dynamics of the system, because your controller is intended to center the user in a certain position. So you're not exciting the system in a very fancy way. But it's good because what you're identifying is exactly what you need for the task at hand. So you're oriented in a closed loop way. Your identification is driven by the actual context that you really need when you will walk on the platform. You will not go away from the platform, so you're restricting the operative condition to what will be the actual operative condition. So there's a good and bad in this strategy. This type of identification is called closed loop identification, in fact. Now, with this experimental test, you do both a modification of the ideal model that you use, so you identify the modification of the model that would fit better what you have done with your controller, with what you're doing, you're collecting from your experimental data, and you do some fitting. At this stage, once you have identified the correction that you need to use to your ideal model, you do a model validation. So at this stage, you use a new set of data, not the one that you use for identification. This is rather standard, I would say, so that you see if you're satisfied with what you have collected about the model. And now you have a new model, identified model. You go back to simulation and you possibly modify the original nominal gains into actual gain, because now your simulation model has changed from an idle one. You're using the model that you have actually identified and already validated in experiment. So you fine-tune your gains, and finally you go back to the real platform, you do performance evaluation, you do a final tuning, which is always necessary for a reason or the other. When you are on field, let's say, there could be a final slide modification of gains, or some changes that you realize are needed in response to the actual performance or the perception that the user is giving. When you have a human in the loop, of course, this final stage is equally important, because human reactions are different from one subject to the other, and you can classify good worker on the platform, bad worker, and things like that. Okay, so let's see very briefly what are the steps in our case. We applied this to the 1D linear treadmill. So we have seen how to design the controller in the idle case, where the model was a simple second-order system, kinematic. We made trial and error with some guidance of control gains. And in order to have a reasonable guidance in choosing the gain, we linearized the closed-loop system. Remember that there is a nonlinear term related to the way in which the saturation function changes the reference position. So once we linearize this and we look at the mapping between, we are already a closed loop system, so our target is to bring the the actual position to a certain location in response to a disturbance. So we are looking to the disturbance input to controlled output transfer function. This transfer function takes on quite complex format. There's a sum of two terms at the denominator, but the denominator in fact is a fifth order polynomial. The numerator is a fourth order polynomial. So in this set you can make a choice so that the result will be a transfer function which will be certainly stable, but we make a choice of placing the poles and also the zeros in such a way that they are all real, so that you have no oscillating transient in principle. And this is the result of this choice. We could have chosen faster poles or slower poles and things like this, but this was a guideline, one possible guidelines for selecting the nominal gains on the initial system. There's one comment here to be looked at. Of course, we would like to have asymptotic stability, but the closed loop transfer function, which we call PS here, we could have called it is WS as it's traditional, but anyway, it's the closed loop transfer function, is not really asymptotically stable because it has one single pole on the imaginary axis, in fact, in the origin. It's one pure integrator left. Now, this should let us worry, but in fact it's not really important. We can remove this from the picture. It's like if we considering not the acceleration as input, but the intentional velocity as input to the system. In fact, as we said, in the most simple response that we can imagine, a step response to our disturbance input, a constant value hold forever of acceleration is not sustainable, while a constant speed of the user is. So if we remove this pole in the origin, we would have a transfer function which is asymptotically stable between the intentional velocity of the walker, which is our disturbance, and the actual controlled position x. We would like that this disturbance has the least effect on the position so that the position can go back to zero or to the reference value that we have chosen, since we are linearizing the closed loop system around zero. So this is our target, bringing it back to zero. Okay, so this just to clarify that this why this pole in zero can be removed from the picture. Now, we assumed, as I said, that if we command velocities, these velocities are immediately realized. Now, there are two directions on the CyberWalk 2D platform. There's the one direction, the x direction of the chain motion, and then there are the y direction of the several, actually n equal 25 treadmills. Now, in the y direction, if you limit your update and your measurement to 50 Hz, so in this bandwidth of the closed loop system, the fact that our commanded velocity are the actual velocity that are being realized is perfectly fine. So we don't have to refine our ideal model with respect to the presence of, let's say, actuation dynamics. The fact that the commanded signal is not really instantaneously realized. On the other hand, along the x direction where a huge amount of mass is moving, we need a larger inertia with respect to the axis of the motors, which are rotating. We need to do some refined identification. So, assuming that our velocity command in the x direction is instantaneously realized, is not completely true. So, with this direction, in this direction, we perform some experimental tests under closed-loop control. And so this main direction will be also the direction of interest. So we move after doing dynamic identification in this single direction. We found out through the use of some MATLAB function from the system identification toolbox, which makes a prediction error estimate for models that are linear and that are expressed in parametric form, the best fit from the experimental data that we collected under closed-loop control with the nominal parameter that we chosen is given by the transfer function on the right-hand side. You see that there's a small pole and there's a limited perturbation by a factor of 2% of the gain of the system, which is not unitary in fact. Now, with this model, which represents the actual dynamics in that direction of our control system, we try to capture, in the model validation phase, new experimental data. So the user went on the platform, collected commands and positions, velocities, and we checked with this new model if we were able to capture this new data. And the fitting was very good. In fact, you can see that the difference between what you can simulate, what you expect to have as commands, and what you have measured in this transfer function, there's a fitting which goes up to 97%, which is quite good. So this comparison is one of the many comparisons that was made using samples from the time domain, samples of data, and overall possible motion that were used for validating the model, the fit was always beyond the 90%. So we accept at this stage the use of this slightly modified model in our control. So we included this transfer function in place of just one within the commanded input and the actual velocity. So with this in mind, we run a new set of control gains in simulation. We included at this stage the presence of maximum perceptual constraint, so maximum acceleration to 0.5 meter per second square, and also maximum jerk, 1.2 meter per second cube, so maximum variation of the acceleration command. And the final gain were the 6 gain that we were interested into, so K1, K2, and K3 for the observer, Kx and Kv for the PD controller, and Kref as gain for the saturation function, which modifies the reference position. And here you see that in a certain motion of the walker, in the one direction of the main direction of the treadmill, was pretty much similar between simulation and experiment. You can see that both the level and the profile of variation of the acceleration and also of the integrated velocity are satisfactory for our purposes. So, at this stage, we move to the two-dimensional final platform. In fact, this is a short video once the CyberWalk platform was rebuilt in Tübingen without the big Cyberneum. There's a huge room, very high. It's a kind of a cube, and the platform was placed there. The Vicon system was mounted. A wooden floor was constructed around the platform, so the platform is all below this higher level. This level is about 1.2 meter or or so from the ground. And here you see the first experiment. Here again is Paolo Buffo walking without a head-mounted display, just to testing what happened. You see that there are some problems. There is lubrication problem also in the system. There are many effects that should be taken into account. Even here, a sudden stop is not the best from the perceptual point of view. So you see that you need some tuning. We don't want to change the whole control scheme, but now we have a controller for the treadmill direction and a controller for the change direction. And these controllers are tuned in a different way, but essentially they are decoupled, completely decoupled at this stage. So this is just to show that something more needs to be done and can be done. In fact, when we get toward the end of the project, we made also a workshop, or we organized a project also, a workshop also with the reviewer and also with external researcher. There were presentations at the end. Many people tried out, including the reviewer, tried out the platform. And this is a video which summarizes one test with a user, not part of the publicum, but not even a user who was a member of the research team, so it was an independent user. So let's see what happened in this longer video, which describe all phases, so the mounting of the harness, and then the head-mounted display, okay, it should be covered as much as possible. In some situation, lights were turned off in order not to interfere with the vision. Then the helmet with balls for localization with through the Vicon system. And now, ready. Turn off the light and the user starts walking. And of course, the platform compensates his intentional motion, her intentional motion. She's changing direction. We don't see here in this phase what she is looking at, but she is walking actually in the ancient Pompeii. I have a later video where this is clear. You can see that now she is walking exactly in the direction of the chain, so the various treadmills are floating below her feet. Now she moves in the direction of the treadmill. You see that the treadmill on top, they move at the same speed, so there's no relative motion, and she stops, she recovers position, she turns in place, but because she's looking around in her virtual world, and now she's going somewhere in one of the roads of the ancient Pompeii. Pay attention how she uses her legs. The mobility is rather stable. See, this is the situation that she's looking at in this moment. See, it's a more complete representation of the building. She's entering in one of these buildings, she's going through the arcades, and so on and so on. I think we are. So this is a stop, it's another segment, but I think that more or less. Okay, this shows what happens below. Below there is all this machinery, the chain is moving the treadmill because the walker is walking orthogonally to the treadmills. Of course, any component in the direction of the treadmill is realized by the treadmill which are on top. Those that are below are being stopped because of the reading from the barcodes to reduce the total amount of noise. The system is relatively noisy, I would say. Okay, that's it. So, as I mentioned, 2 out of the 3 reviewers of the project were satisfied. 1 was not able really to walk on top of this platform because of some seasick phenomena. Never was able to start moving with some decision. Okay, so when the project was over, quite about at the same time, with our coordinator, Professor Mark Ernst, prepared also some dissemination package, of course, and this is a video that was mounted by National Geographic. A short video is 1 minute and 30, which illustrates the whole picture in a different way than we do in our scientific content. So there's more a storyline told. So there's an audio here, so please listen also to the audio. I will not talk on top of it.
So you want to visit the ancient city of Pompeii, but you just don't have the time or money to get there? One group of scientists may just have a solution for you. It's called the CyberWalk, a system that allows users to walk freely through a variety of virtual worlds. Its display gives users a visual experience of Pompeii as it would have looked before its destruction in 79 AD. The head-mounted gear is connected to a computer that constantly updates the user's view of the virtual environment, creating a seamless sightseeing experience. But the scientists also wanted users to actually walk through Pompeii, which proved to be a tougher challenge.
Yeah, we thought, how can we achieve that? And first of all, of course, what you need is some kind of a treadmill, but a treadmill that can go in any direction, not only like in a gym that goes in one direction, you need something that goes in both directions, an omnidirectional treadmill.
The developers say the treadmill provides an interaction between perception and locomotion, helping to recreate the experience of Pompeii as it once was.
Pompeii was picked because it's an architectural site that you cannot walk anymore through because it doesn't exist anymore. Therefore, it's a great showcase to demonstrate what virtual reality can do. You can go 2,000 years in the past and explore a city that doesn't exist anymore.
The scientists believe the technology has many potential applications, which include rehabilitation and training in virtual environments. But for now, bringing Pompeii back to life is a good start.
Okay, so I must say that it was quite successful as a project. Indeed, Pompeii exists even now, but not in the form that it used to be before the volcano eruption. So what to say next? Things were not completely satisfied for a number of reasons. So this short video, this is me on the platform exactly at the end of the project review, so everybody was satisfied, and I finally had the occasion of trying myself. I never tried it before, so this is my first walk on the platform. And it was a very nice experience. I mean, I really went through the road of Pompeii. I entered through some buildings. I tried also to cross walls, and nothing happens. Of course, there's no haptic feeling in that context. You just pass the walls and you find yourself in a new room. So this is not really realistic. But so I really enjoyed this. But looking afterward at the video, I noticed a particular case, a particular situation. So here I'm starting walking, not too confident at the beginning, but after a while, I completely forget to be on the platform, and I start walking. But look at my legs. Look at what I'm doing with my feet. From time to time, I'm crossing my feet. I never realized this while walking. I only realized this afterward, seeing myself on the platform. So why does this happen? The reason is very simple. Remember that we have we have done a synthesis which was independent of the two directions. So we have one controller controlling motion of the chain, so of the bulk of treadmill, and one other controller controlling motion along the treadmills. And of course, each has some reference position in the x and y direction, but there is no interaction between the two, not at all. However, this is not the way in which we feel acceleration. So, look at this picture on the right-hand side. The x and y are exactly the direction of the treadmills and of the chain. While we are having some orientation, let's say I'm using the same notation that we used for the cyber carpet. So there's an angle theta w of our main sagittal axis with respect to the x-axis. So we are walking in the xw direction, not in general in the y or in the x. While we are using more or less the same gain in the x and y direction because we designed this independently. So our controller looks like this. No? We compensate for the intentional acceleration, we reduce the intentional velocity, and we try to bring the position along to the reference position, which is not at the center of the platform, but this is not really relevant at this stage. And the same for the y direction. So we make no distinction. If we have a large error in x or in y, we treat them exactly in the same way, modulo a small difference of the gain kp in the two, because we tune the controller in a slightly different fashion. But we treat them essentially in the same way. However, what happens while we walk? When we walk straight and we have a perturbation, so let's say it's somebody pushing us in the direction where we walk, either against the walking or in favor of the walking, we have an easy way to recover balance. So we can tolerate acceleration, either intentional, pushing. Here nobody is pushing us, but the base is moving. So we have a disturbing acceleration because of the compensation that the platform is having to bring us back to the center of the platform. So we are less sensitive in that direction, while if somebody is pushing us on the side, in order to keep balance, we typically cross legs while we're working. Of course, we would make a step aside if we were able, but since we are walking, the best that we can do is to do this crossing of legs in order to recover this side balance. Why? Because we are more sensitive. It's not our natural direction of motion. So this simple observation brought us to think that when we are recovering, recentering ourselves with motion of the platform, we should be very, very careful in recovering side acceleration to the walker, so in the y direction, then in the direction where the walking is going, so in the xw direction. Which means that we can tolerate larger control gains, which recover the position error, in the sagittal plane than in the transversal plane. Now, in order to do this, we have to update our gain depending on the orientation of the body, or better said, the orientation in which we are walking. So we would need at this stage, for the first time explicitly, not only the position of the walker, but also the orientation of the body, or better said, the orientation in which the human is walking. Not really the head, because I can walk in this direction, having the head rotated. This will change what I see in my head-mounted display, but has nothing to do with the direction where I'm going. So, at that point of the project, it was too late to implement what we had already implemented through the particle filter and to the use of this ellipsoid and the head, a circular head. And we had a method that was able to track position and orientation of the body, so of the main direction of motion of the user. You remember that video and that experiment. But here, we didn't have an overlooking camera, we had the Vicon system, so it was too long really to implement that. So, in order to test this idea, we made some motion where we asked intentionally the user to keep the head in the direction where they were walking. So, not rotate the head in this way. So that from the information that we used for the virtual immersion on the pose of the head, we had also the pose of the body and so the direction of motion. So we can identify easily where XW was. Now, what we do for this? Of course, this could have been done if we had more time. But with this information, so once we have the theta W angle, then we can tune the gains in the following way. We see an error along the X and Y direction. We rotate this error from the XY frame into the frame which is attached to the human. So with the XW axis and the YW axis. If this rotation is, if this orientation is characterized by the rotation R of theta W, and this, what you see on the slide, is a planar rotation, so it's a 2x2 matrix. We are not rotating in the 3D space. So, if this is the orientation of frame W with respect to the XY frame, then in order to map an error which is expressed in the XY frame into the W frame, we need to multiply by R transpose. So this R transpose is on the right and multiplies the error along X and Y. Once the error has been rewritten, expressed in the rotated frame, we apply a diagonal matrix KPW. And in this diagonal matrix, of course, the gain on the XW axis will be larger than the gain on the Y axis. So we will react more nervously, I would say, or more promptly to error along the sagittal direction rather than error on the side direction. So at this stage, we have constructed a control reaction, some form of acceleration. But the acceleration cannot be applied in XW and YW because our commands are along X and Y. So this action, this command, should be rotated back to the original X and Y axis. So our total gain matrix is no longer diagonal in XY, is diagonal in XW and YW. So it's the result of orientation-dependent gain, Kp of theta W. A very simple idea. In robotics, this is done all the time. In this human-in-the-loop application, it was an idea that needed to be explored. So first of all, we did some simulation. Okay. Now this is a simulation in which you see a square, which represents a blue square, which represents the platform. The center of the platform is the black full circle. There will be a brown empty circle, which will represent the modified reference, no? Because here we apply both in the X and Y direction this concept that we have seen of allowing more space. While the blue circle with a pointing arrow represents position and orientation of the walker in motion. There are two videos, so two different motion. One is more regular, the other is more random. In fact, it's collected from an experiment and then reproduces in simulation. In the first video, the walker is placed really at the boundary, right boundary. You may recognize the arrow at the right boundary of the platform, pointing in the, let's say, straight direction, upward with respect to the screen. Okay. So let's see what happens now. Let's focus on the slide only. So this is the motion. You see that it started moving and the reference went in front, and we are getting to the right in the orientation of the worker, we are getting to the reference, while on the side, we take more time. You see, it's quite slower. In fact, only at the end, we recover the side error, while the error along the direction where the user is pointing is being recovered faster. Now you will see even more clearly what happens here. The previous motion was a sequence of straight line along the side of a square, most probably, while here it's a more continuous one. So you see that you capture, if you project the error along the arrow, you will see that the tangential error, so the error along the arrow, sorry for the confusion, is goes to zero, while much slower goes to zero, the error along the orthogonal direction, which is the side direction for the user, which is the one where the gains were tuned down. Remember, the fact that there's a reference point which is not at the center is to allow more space beyond the user in order to have lower acceleration when the user changes suddenly its speed, so it stops or it starts. Now, this was in simulation. We were convinced that this was going to work, but how to check this on the platform? So this is one of the latest experiments that we did. It's an IROS paper in 2009, and in this case, we made an experiment with different users, first using constant control gains along the x and y axis, and then using this rotation idea. Here you will see side by side the actual experiment and its representation in this MATLAB style view, which is the same one that we use for simulation. You see here, again, on the side, the walker goes to the red arrow point without changes of gains according to its orientation. And this is why, when he changes orientation, because of this, there will be a same acceleration on the side, and in order to recover stability, without really intention, the user is crossing his legs. So we use the crossing of legs, this is a slow speed, to represent the fact that the side acceleration in this transient was too large. Now, the second experiment is using the variable gains, or let's say constant gain, but along the walker x-axis and y-axis, and then rotated in order to be implemented along the x and y-axis of the platform. Same situation as before. Now the varying gain according to the orientation. Now you see that the user changes direction, but there's no crossing at all of the legs. You see that the side recovery is much slower than the sagittal recovery. Only now the user is in the position, the reference position. And now again, changing direction, no leg crossing, as a visual representation of the fact that there is less side acceleration applied to the walk. Now, this is the visual part. Of course, the user, we tested this on different persons. The user mentioned that it was more comfortable. They were exposed to both situations, and they felt that this change let them walk in a more comfortable way. Okay, I think quite a simple idea which takes into account some perceptual constraint on the human being, something that would not be important if a robot was, or maybe a robot was let's say, a tracked vehicle was mounted on the platform. Again, this is a generic random walk, so the user is immersed in some virtual reality. It's going, stopping, turning. But no big changes in this case. Okay, we are almost there. Just to understand that there's a slower dynamics of error recovery on the side. And this is quite clearly in these images. Then it stops and then starts again. The video is almost done. You see that now on the side there's a recovery. When the user stops, the video was interrupted at this stage. Okay, so we end this long presentation. What did we learn from this experience from the different platforms? Well, one typical case is that, let's start with the second comment. If the update of measurement and command is too slow, then typically the platform will experience a jerky and oscillatory control. And this would affect, certainly, the perception of the user. On the other hand, if you update things at a faster rate, you have a better performance, but this would allow also faster control reaction if you don't impose acceleration and jerk limits, because you may not meet the perceptual or the comfort constraint, let's say. Now, many changes can be done. For instance, we may have slow reaction when the user is still or moving at a slow speed, while gain may be increased when you're moving, because when you're moving, especially if you're rotating your action in the sagittal and transversal direction in a different way, but you're even faster in the sagittal way, when in the sagittal direction, when you're moving fast, then I would say that this may be a good improvement, because when you're moving fast, you're less sensitive to any disturbance. This is the whole story. You should always avoid discontinuity in acceleration and jerk, if possible. And you may have also a learning phase. A learning phase depending on the walker, on the magnitude of his intentional velocity. This was partly done with changing the reference position, but it may affect in a time-varying way also the gains. The idea of having classes of gains tuned for a user which is an experienced one, or a first comer, or depending on the first trial, we can also classify from a perceptual point of view the way that the user is changing his walking pattern. All this can be matched into different controllers, or control gains, better said, for the platform. Let me conclude also with a comment on the other platform that we have seen, the omnidirectional one, the non-autonomic one, the ball array platform, by saying that the analogy with wheel mobile robot control is quite interesting. In fact, although we did not apply it, later on we used a regulation controller in order not only to bring the walker at the center, but to bring the walker at the center with a given orientation. We were not really interested in doing this, but using the analogy with mobile-wheeled robot control, we could do this by suitable maneuver. What is the difference? The difference is that the analomy in the case of wheel mobile robot comes from the fact that the user the wheel mobile robot is moving on a flat ground, and a fixed ground, I would say. In our case, we turn things on the other side. We have a fixed walker and a moving ground that has non-aerodynamic constraint. So as long as the walker is not moving, the problem is perfectly dual to the case of a fixed ground with a wheeled car. So we could park the car with maneuver and reach some position with given orientation. Similarly, turning things around, we could have a user standing still and bringing it back to the center of the platform, of that platform, also with a given orientation. However, as soon as the user starts walking, this analogy is lost, or better said, it's like having a wheeled mobile robot moving on a ground which is moving itself in an unknown way. This is why we needed some observer of this intentional motion to be complemented to a control law which is made in feedback. In our case, our target was only regulation of position. If the target would have been regulation of position and orientation, then some changes should have been added to the feedback controller that does this for wheel mobile robot, probably using the disturbance observer. In the case of the omnidirectional platform, so the large CyberWalk platform, this problem of orientation has no sense, because the platform, no matter what we do, is not able to change the orientation of the walk, just to displace him in any direction, X and Y, or combination of it. So this concludes this presentation. Thank you very much for listening.